Hi everyone, and welcome to our final webinar of our series. We are going to be presenting Plume dynamics, influence of geological heterogeneity, solubility and grid resolution on CO2 storage efficiency and trapping, and it's presented by my colleague Serkan. The webinar will offer insight into how tNav advances understanding of CO2 plume behaviour, revealing how geological variability and composite sealing systems shape storage security and trapping efficiency. If you could just move on to the next slide, please, Serkan. Just to run through a few details for the webinar, so everyone is automatically muted. If you do have any questions, you can ask them in the chat function bot, and we will run through some questions and answers once Serkan is finished presenting. This session is recorded and will be uploaded to our YouTube channel after, and if you have any further questions or anything, you can get in touch with us on the email address below. Now I'll pass over to Serkan. Thank you.
Thank you, Robin. Welcome everyone to today's webinar. Before I start talking about the subject matter, I just want to briefly mention the fully integrated nature of tNavigator. We can do everything from geology and geophysics, structural modeling, reservoir characterization, dynamic modeling, simulation, uncertainty and optimization, and well completion and surface modeling all in one software. It's truly integrated. Nature allows different disciplines to work together under the same hood. And now the agenda for today. We're going to be focusing on CO2 storage, so it's probably a good idea to just talk briefly about how CO2 is stored. Then we'll briefly mention previous work done by AP, Bump and colleagues on composite confining systems, what they are. And then we're going to talk about our work, which is an extension of this previous work and a model description of what we've done, and then share some results with you and leave at the end with some food for thought. So how is CO2 stored? We have in this case, brine that we're going to be injecting CO2 into, and we have our injection well on the left-hand side. And as we inject the CO2 into the reservoir, into the saline aquifer, the free CO2 is going to start migrating upwards. And as it moves through the reservoir, it's going to meet the impermeable seal, and some of it is going to be left behind, which is going to be the residually trapped CO2. This is due to hysteresis and relative permeability endpoints. And then some of that is going to be dissolved in the water. So that's going to be CO2 saturated in brine, and you can see some of those nice dissolution fingering effects on the right-hand side. And obviously, the bulk of it is going to be in the structural trapping, at least in this picture, which is what you see in green. So the study by Alexander Bump and his colleagues focused on differentiating the two types of seals and focusing on obviously the composite confining part. So on the left-hand side, we have the conventional seal, where we have a competent seal, which is supposed to hold all the CO2 structurally in place below it itself, so within the injection zone. And the alternative to that is the composite confining system, where we don't actually have this seal completely blocking everything, all the CO2 keeping it under the seal, but some of it actually exudes through, and some of it is then baffled by this confining zone. So here we have several sand bodies, some silt, some shale. Nothing is really laterally continuous, but it's overall as a system, it impedes the movement of the vertical movement of CO2 enough that it also serves as a seal. So this is the general idea behind it. They've also done some lab scale, tank scale bead pack experiments. So the scale is here at 60 centimeters. And you can see the movement on the right-hand side in B, the movement of CO2 upwards, and how it is actually impeded or slowed down by these several fine-grained layers. So the multiple continuous barriers effectively reduce vertical permeability. That's one of the outcomes from here. And of course, the longer the flow path, the more dispersed the CO2 plume is going to be increasing the trapping opportunities as well. And here are some simulation results from them, comparing two different cases of 5,000-foot average barrier length to 2,000-foot average barrier length. You have the phase distribution, the CO₂ at the end of injection, and also post-injection, which is 100 years in their case. So what we decided was to actually look at this in more detail and to work with a range of parameters. So we're looking to look at the effect of heterogeneity in 3D, the effect of numerical parameters and fluke properties. So some of the variables we'll be looking at is the fraction of sand, the variogram major range, the range ratio, so it's the major to minor ratio, the variogram vertical range, KVKH, salt molar fraction, and grid parameters, which is basically the resolution. On the right-hand side, you can see the screenshot from the workflow that we used. So all the different steps of calculating the facies, pore-perm relationship, creating endpoints, and adding the aquifer, and so on. The model description is we kept a quite simple model for conceptual reasons. So we have a model of 6 kilometers by 6 kilometers by 0.2 kilometers in the vertical direction. We start with an initial pressure of 200 bars. We're using the CO₂ store keyword for dissolution modeling. And what's quite important is that we have an aquifer that allows for backflow, which means that the pressure within the simulation box is not going to be increased artificially when compared to what would be happening in nature, thereby affecting our results. And we're going to be injecting 5 million tons of CO₂ over 10 years. With a post-injection period of 500 years. And we have two types of relative permeability curves, drainage and imbibition for two facies. So on the left-hand side, you can see the drainage and imbibition curves for our sand facies, and on the right-hand side for the shale facies. The output, just one example, looks like this. So we're looking at the sand and shale distribution. We purposefully kept it to only two facies types to be able to control the parameters more easily, and also be able to come out with simple learnings and a good narrative at the end of it. So we have two regions here, two zones. The bottom zone is where we'll be injecting, and that's called the reservoir zone, and it's always completely sand in all of our cases. And what we do is actually modify the heterogeneous zone, which is the second zone on top. So all the parameters I mentioned will be affecting this zone only. Some sample properties. So facies distribution on the top left side, which we've already seen. Bottom left is porosity. Notice that even though we have sand everywhere in the first zone, within the reservoir zone, we also have varying porosity. And as a result, we have varying permeability as well. And the regions is important too. So we have the bottom region, number 3, which is the reservoir. The heterogeneous part is number 2. And on the very top, we have another fit number, which we've added for monitoring purposes. So later on, when we talk about the results, this is the zone that we'll be looking at in terms of whether there's any CO₂ breakthrough or not. So here we present two representative examples, just to give you the idea of what we're doing. We kept the sand fraction the same between these two examples, but we're varying the major and vertical variogram ranges. So on the left-hand side, we have 800 meter laterally and 200 meter vertically correlation within the variogram. On the right-hand side, we have 400 laterally and 10 meters vertically. And within the red circles, you can see the behavior, the difference in behavior here in terms of facies distribution. So on the left-hand side, we have more laterally extensive bedding, which would then impede vertical movement of CO₂ plume. And on the right-hand side, we have more blobby distribution of that. So we'll see some results of this later. So what we're ultimately interested in is basically proven the concept of Bump et al. Saying, can heterogeneous zones prevent CO2 from escaping? Of course, it's a complex question. It's not just a single parameter. And for that, we're breaking down the results into several sections, looking at the fraction of sand, the lateral extent of shale barriers, the vertical extent of shale barriers, the KV/KH ratio, and salinity as well, which has an impact on the dissolution. And numerical effects can also be extreme with large fluid cells, which we'll also have a look at. So the first plot I want to share here from the results is the effect of the fraction of sand. So what we're doing here is keeping everything else constant. So this means we picked a major variogram range of 500 meters, a vertical range of 5 meters, KV/KH ratio of 0.1, and a 1 molar percent sodium chloride concentration for salinity. And we're changing the fraction of sand from 0 to 100%. Well, not quite, but almost. And what we see here is on the y-axis of the plot, number of moles of CO2 in million kilomoles. And we can see a clear distinction between those models on the left side of this line and those on the right side of this line. So left side means that CO2 is contained. So within the very top layer, we don't actually observe any CO2 after 500 years. And on the right-hand side, we have increasingly more and more CO2 showing up into this top region with increasing fraction of sand. So this makes sense, obviously, logically. But if we look at the actual model, so here we picked 3 different ones. We can see also the correlation with the distribution of the facies. Makes a much clearer picture of what we're looking at. So then the next question was the effect of the major variogram on the amount of CO2 in the top region. And this is a zoomed out view of the variogram range modified way past the boundaries of the model itself. So just we wanted to have a look if it actually has any impact. And as expected, we would see some point of diminishing return. For example, we actually have CO2 contained up to a certain amount. So this is something like 1,000 meters lateral extent, above which CO2 is contained, regardless of how much sand fraction we have in the model. So if we zoom in here a little bit, we see a very nice correlation. In green are the variants with 60% sand fraction. In blue is 50%, and it keeps going down from there to 40 and 20%. The first thing to notice is that, of course, what we've seen before, as we increase the sand fraction, we have more CO2 observed in the top layer. But also the point at which we can say that this system serves as a composite confinement increases with increased sand fraction. So, for example, if we're at 40%, we only need 320, 330 meters lateral extent to actually have this whole system serve as a seal, whereas at 60%, we need higher lateral variogram range, about 900 or 1,000 meters. Now looking at the vertical variogram range, here we've kept another base case of 60% sand and 700 meters lateral extent of the variogram, and KV/KH and salinity is the same. So here what we're doing is increasing the vertical variogram range, and starting from 2, where we have laterally extensive bedding of the 2 facies, and where we actually don't have any CO2 breakthrough in the top layer. And as we increase it, we of course have more and more CO2 breaking through. So just to show the effect of the facies here, I've picked 2 of the variants here, and the one in the middle is the one that looks more blobby, allowing for more vertical connections, and for the CO2 plume to actually travel vertically more easily. The effect of kVkH, this combined two separate experiments with different ranges, but the story is the same. So we have constant fraction of sand at 60%, 700 meters major lateral range of the variogram, and 5 meters vertical, and 1% sodium chloride concentration. And we can see that at very low kVkH, as expected, we have no CO2 breakthrough in the top layer. And as we increase it, we have more and more CO2 in the top layer. There's an interesting inflection point somewhere around 0.1, somewhere between 0.1 and 0.2. So that's also interesting to note. And from the parameters, last but not least, is the salinity. The effect of salinity is also actually significant. So we have 60% sand here, and keeping some of the other variables here constant. On the left-hand side, we're modifying the amount of salt dissolved in the water to start with, which impacts the dissolution. So we're ranging from 0.05 almost to 0.005 to 0.05. And you can see that as we increase the salinity, we have more CO2 actually arriving in the top part, which means that our dissolution actually is going down with increased salinity. So when less is dissolved within the plume that's left behind, then more obviously is going to stay in the free gas and actually make it to the top layer. So here's a comparison again for different salinities. There are three plots here. We have on the left-hand side the dissolution, so a number of moles of CO2 in water. In the middle, we have number of moles of CO2 mobile in gas, so this is the free gas. And on the very right-hand side, we have the number of moles of CO2 trapped in gas, so this is residual trapping. And for the dissolution, you can see the inverse correlation. So as we increase the salinity, we have less dissolution ongoing. And for the other two, we have the opposite effect. So as we increase the salinity, we have more free gas and more residually trapped gas. So how big is too big when it comes to cell size? These are two models compared with one another from a paper of Yene et al. And some of our colleagues from SP Europe Energy Conference in 2025 in Vienna. And on the left-hand side, we'll have a fine grid. And on the right-hand side, we have a coarse grid. And you can see the impact very clearly in this nice little video. So this is to make the point that at some point you stop seeing some of these effects if your grid is too coarse. So from the same study, we can look at the relative contribution of the different trapping mechanisms in the fine grid, which was 20 by 20 by 1 meter cell size, and in the coarse grid, which is 200 by 200 by 4 meter cell size. And you can see a large difference in the different trapping mechanisms. So dissolution obviously is affected, which is the dark purple part at the bottom, but more importantly, the residual trapping and the free gas are actually affected by a lot. So this again points to the need to look into more depth when it comes to the grid size, the effective grid size. So the key takeaways and future work. So first of all, the composite confinement can actually substitute a competent cap rock under the right conditions. And characterizing this is crucial to evaluate whether this is possible or not. So sand fraction, variogram ranges, kVkH, and fluid properties all play a significant role. So if there's too much sand, then containment of CO2 will not be effective, regardless of what you do with the other parameters. Lateral extent is more important than vertical extent of the barrier. Lower kVkH is favorable, and salinity reduces the solubility, so thereby leading to a higher risk of leakage. In the future, what we'd like to do is look at the effect of cell size for all of these cases that we've looked at. So currently, we've only done it for a subset of some of the results that we've shown here. We also want to run a full probabilistic study with all the variables changing simultaneously. So in this first step, we wanted to modify them one at a time to actually come up with some conclusions from each different part. But doing a probabilistic study is going to be a lot more inclusive of the different variables. And we also want to introduce more detailed phase shear models and also vary the capillary entry pressures. Our team, so Serkan, myself, and Marcus Duffy, our geology team lead, he came up with the geological concepts. Mark Lakos, who's also presented a version of this presentation at the GET 2025 conference, who's a senior reservoir engineer, and Soren Sirbu has also helped with reservoir engineering support. Thank you for listening. And if there's any questions, maybe Robin will fire them my way.
So much, Serkan, for a great presentation, and thanks to everyone for attending. I hope you've found the session beneficial. You will receive a follow-up email that contains a short survey just for some feedback, and we would really appreciate if you could take a minute to fill that out. There has been a couple of questions, so I'll just run through a few of them with you, Serkan. The first one is, for the amount of CO2 in the top region, is the distribution sorry, it's just moved down because someone else has just put one in. Is the distribution of that focused into a single area or region of CO2 breakthrough, or do you see multiple pathways all reaching the top layers for different sand distribution scenarios?
So the graphs don't differentiate, obviously. That's if it shows up in one block somewhere, then it's registered as a whole region. However, depending on the distribution via the different variograms, it's possible that there will be several pathways. So you could easily imagine several chimney type of vertical conduits, which would then be connected to the reservoir zone. And that could be that you actually have multiple breakthrough zones. That would be in the case of you know, having a high vertical variogram range, for example.
The next one is, can you couple temperature and reactive materials to your simulation? As you know, in many cases, we may inject cold CO2 into a hot aquifer. Also, reservoir sands and cap rocks may have reactive materials, e.g. carbonate.
Yes, so we can do thermal CO2 store as well, which includes some basic reactions. But if you have bespoke reactions that are not part of this preset physics within the CO2 store keyword, you can also do a fully thermal model. And in that case, you can also pick your EOS from several different options.
Thanks, Serkan. Sorry, I'm just having a look through other questions. We've got tNav can include Joule-Thomson effect.
Yes, the Joule-Thomson effect is completely accounted for within tNavigator.
And one more here is, how do you generate reservoir properties for the coarse model? Is it by upscaling the fine model?
It's rather the other way around, because what we wanted to do was we wanted to actually make sure when we change. So this is specifically talking about the grid, changing the grid size, right? So we wanted to look at only the effect of the grid size, which means that if we upscale it, we get different properties. So we actually, when we were comparing those, we looked at the coarsest, most possible model, and then did global LGRing on that, so that we actually have the same properties in any given XYZ coordinate, so that we can take out any result differences due to actual property differences.
Thanks, Serkan. I'll just finish up with one last question, and if there is any unanswered questions, the team will get back to you individually. So to finish up, we've got, is there a recommended grid resolution for capturing dissolution fingering?
Maybe I have just 1 second if I can. Yeah, so it's not from this study, it's from a previous presentation that we had last year, but this compares several different grid resolutions in cross section. So the recommended is not, there's no, magic number for that. But I would say if you're above 100 meters in the horizontal direction, you're not going to see the dissolution fingering effects, for example, which is clear in here, right? Vertical is seems to be less sensitive, but even then, when you're at 4 meters, you can see a difference to when you're at 1 meters, right? So I would say somewhere below 100-meter horizontal resolution and not more than 2 meters in vertical is a good number. Obviously, if your model is huge, then you're going to have to take some other shortcuts or move to larger hardware.
Perfect. Thank you so much, Serkan. We'll just wrap it up there. If there are any unanswered questions or anyone does want to know any more information, you can reach out to the team directly. As I said at the beginning, all of our webinars are posted to our YouTube channel, so you can find them there and you will receive a short feedback survey. But again, if you have any questions, then please just reach out to the team, and thanks so much for attending. Thank you.
Thank you for joining, everyone.